It's not a meteor. It's not an asteroid. It's not an engine failure, or a hull breach, or a computer that stops answering. It is light. It is the same star that warms your face on a July morning, the one you were told never to stare at, the one that has burned steadily for 4.5 billion years. And in low Earth orbit, in the space of about 20 minutes, that star can turn a spacecraft into a place you have to run from. Not run outside. There is no outside. Run inward, deeper, toward the thickest wall you can find, and wait. And the terrifying part is this. The astronauts who have done it were not fleeing something they could see. There was no alarm you'd recognize, no fire, no smoke, no shudder in the structure. The station looked exactly the same as it had an hour before. The only difference was a number on a screen in Boulder, Colorado, and a voice from the ground telling a crew of professionals to put a wall of water and metal between their bodies and the sunlit side of the sky. They had, in some cases, less than half an hour of warning, and the thing they were hiding from was already there. Today we break down everything: what the sun actually throws at a human body, why the human body has no defense against it, the specific days when crews were ordered into shelter, the near miss in 1972 that would have killed men on the moon, and what happens when the next one arrives, while people are further away than anyone has ever been. No filler, just the facts. No guessing. Start with the thing you already know and get it wrong anyway. The sun is not a fire. Fire is chemistry. The sun is a fusion reactor with a mass of roughly 2 times 10 to the 30th kilograms, converting about 4 million tons of itself into pure energy every second. Its visible surface, the photosphere, sits at 5,772 Kelvin. That is the part you see. That is the part that is calm. Above it, the corona, the faint halo you only glimpse during a total eclipse, runs at over 1,000,000 Kelvin. Physics still argues about exactly why. The outer layer is 200 times hotter than the surface beneath it. That heat is not the danger. The danger is magnetism. The sun does not rotate as a solid body. Its equator completes a rotation in about 25 days. Its poles take closer to 35. The plasma inside is electrically conducting, so it drags magnetic field lines with it, and those field lines get wound, stretched, twisted into knots that store energy, the way a coiled spring stores energy. Sunspots are where those knots punch through the surface. They look dark only because they are cooler than the plasma around them. They are cooler because the magnetic field is strong enough to choke off the heat rising from below. Eventually, a knot snaps. The field lines reconnect into a lower energy configuration, and the difference is released in seconds. That is a solar flare. The largest ones dump energy on the order of 10 to the 25th joules. For scale, that is comparable to detonating billions of megatons of TNT, all at once, in a region of space larger than several Earths. The light from it, across every wavelength including X-rays and extreme ultraviolet, crosses the 93 million miles to Earth in 8 minutes and 20 seconds. There is no early warning for the light. By the time you detect the flare has already arrived. But the light is not what the crews hide from either. Here is the mechanism, and it is simple. When that magnetic snap occurs, and especially when it is paired with a coronal mass ejection, a billion-ton cloud of magnetized plasma blown off the sun's outer atmosphere, the shock front accelerates protons. Ordinary hydrogen nuclei, stripped of their electrons, are kicked up to a substantial fraction of the speed of light. Some reach energies above 1 billion electron volts, and unlike the plasma cloud, which takes anywhere from 15 hours to 3 days to cross the distance, the fastest of these protons arrive in under 30 minutes. That is your warning window, not days. In the worst events, 20 to 30 minutes between the flash and the flood. This is called a solar particle event, and it is the single acute radiation hazard in human spaceflight. Not the only radiation hazard, but the only one that can go from background to life-threatening while you're finishing a sentence. Understand what a relativistic proton does to tissue. It doesn't behave like light. It doesn't warm you. It punches through the wall of a spacecraft, through a spacesuit, through skin, and as it decelerates inside a body, it strips electrons off every molecule it passes. Water becomes reactive fragments. DNA strands break, sometimes both strands at the same position, which is the kind of damage a cell struggles to repair correctly. One proton is nothing. Your body absorbs cosmic radiation constantly and repairs it constantly. The problem is flux. A major event delivers, in hours, what a person on Earth's surface would accumulate over decades. Earth protects you from all of it, and it does so with two systems you never think about. The first is the magnetosphere, generated by convecting liquid iron in the outer core, extending roughly 60,000 kilometers toward the Sun and stretching into a long tail behind. Charged particles hitting it are deflected around the planet or funneled toward the poles, where they collide with the upper atmosphere and produce aurora. That green and red light you'd travel to Iceland to photograph is the visible receipt for radiation that did not reach you. The second system is the atmosphere itself. About 10 tons of air sit above every square meter of ground. In shielding terms, that is equivalent to roughly 10 meters of water. Nothing a spacecraft carries comes close. The International Space Station, orbiting at approximately 400 kilometers, is above almost all of the atmosphere, but still inside the magnetosphere. It gets the second layer of protection weakened, and the first layer intact. That is why the ISS is survivable at all. It is also why the ISS is not safe. The proof is in the daily numbers. A person standing on Earth receives an average of about 2.4 millisieverts per year from natural background radiation, according to UNSEER. An astronaut aboard the ISS accumulates roughly 0.3 millisieverts per day. Do that arithmetic. A 6-month increment delivers somewhere in the range of 100 to 200 millisieverts, depending on solar conditions and orbital geometry. That is decades of ground-level exposure compressed into half a year, and that is on a quiet sun, with no event at all. There is also a specific place in that orbit where things get worse, and it has a name: the South Atlantic Anomaly. Earth's magnetic field is not perfectly centered on the planet, and off the coast of Brazil, the inner Van Allen radiation belt dips closer to the surface. The ISS passes through it several times a day. Instruments log the spike. Crews have described seeing flashes of light with their eyes closed while transiting it, a phenomenon first reported by Buzz Aldrin on Apollo 11 and studied ever since. Those flashes are heavy charged particles passing through the retina and, in some cases, the optic nerve. The crew are seeing individual cosmic rays, not metaphorically, physically, which brings us to the belts themselves, because they explain something about the entire history of human spaceflight. James Van Allen discovered them in 1958 using a Geiger counter aboard Explorer 1, America's first satellite. He found two donut-shaped regions of trapped charged particles encircling the planet, the inner belt beginning around 1,000 kilometers up, and the outer extending past 30,000. Every human being who has ever left low Earth orbit has had to pass through them. Only 24 people have. All of them flew in a 39-month window between December 1968 and December 1972. The Apollo crews got through by trajectory. Flight planners chose paths that clipped the thinner regions of the belts at high speed, minimizing transit time to under an hour in the worst zones. It worked. Apollo mission doses were, in the end, modest. Apollo 14's crew recorded the highest average at roughly 11.4 millisieverts for the entire mission. That is less than a single ISS increment. The engineering was sound and the arithmetic was correct. The arithmetic did not cover the sun deciding to fire. Now we get to August 1972, and this is the part of the story that professionals in the field still describe with a particular tone of voice. On the 4th of August 1972, active region MR 11976 produced one of the most intense solar particle events ever recorded by instruments. The proton flux at Earth rose by orders of magnitude. The event was fast, it was hard, and it lasted for days. Apollo 16 had splashed down on the 27th of April 1972. Apollo 17 would launch on the 7th of December 1972. The August event fell in the gap between them, not near the gap. Squarely inside it, with 4 months of clearance on either side. No human being was outside the magnetosphere when it happened. The obvious question is, what would have happened if someone had been? Analyses have been run repeatedly since, and while the exact numbers depend on assumptions about shielding and event spectrum, the conclusions cluster. A crew inside the command module would likely have received a dose in the range that produces acute radiation sickness. Vomiting, fatigue, a collapsing white blood cell count. Survivable, probably. With medical care they would not have had for days. A crew on the lunar surface in a spacesuit, or inside the lunar module, whose walls in places were thin enough that a screwdriver could have gone through them, faced estimates running into several sieverts to the skin. That is the territory where survival stops being the assumption and starts being the question. And there is a detail from that same event that has nothing to do with astronauts and everything to do with how little we understood it at the time. In 1972, the United States Navy had seeded the waters off Haiphong, North Vietnam, with magnetically triggered sea mines. In early August, U.S. air crews reported watching dozens of them detonate spontaneously in open water with no ship present. The cause was classified as unexplained for decades. In 2018, a team led by Dolores Knip published an analysis in the journal Space Weather, concluding the detonations were triggered by the geomagnetic disturbance from the solar event. The sun swept a minefield. It did so from 93 million miles away, and nobody made the connection for 46 years. What this means is straightforward, and it is not comfortable. The Apollo program did not survive a solar particle event. It avoided one. The margin was 4 months, and 4 months in a program that ran for 39 is not a safety system. It is luck, and everyone involved has since acknowledged as much. So the procedures that exist today were written by people who understood exactly how close that was. Move forward to late October 2003. Solar cycle 23 was past its peak, and, by every reasonable expectation, winding down. Instead, 3 enormous active regions rotated into view and produced a sequence of flares, now known simply as the Halloween storms. 17 major flares in 2 weeks. On the 28th of October, an X-17 event. On the 4th of November, a flare so intense it saturated the X-ray sensors on the GOES satellites, which physically could not record a value that high. Reconstructions place it somewhere around X-28, possibly higher. It remains the largest directly observed solar flare in history, and the instrument built to measure flares could not measure it. Aboard the International Space Station were 2 men. Expedition 8, Commander Michael Foale of NASA, and flight engineer Alexander Kaleri of Roscosmos. 2 people, on a station roughly the size of a 5-bedroom house, several hundred kilometers above a planet that was about to be hit repeatedly. Ground controllers instructed them to shelter. That word does a lot of work, and it is worth being precise about what it actually meant. There was nowhere to go. The station has no radiation bunker, no lead-lined room. What it has is variation. Some modules are more shielded than others because of what surrounds them. Foale and Kaleri moved into the most protected region available to them in the Zvezda service module, an area where the station's own equipment, storage, and water supply sat between their bodies and the outside. They positioned themselves behind their own cargo. They stayed there through the worst of the flux, monitored their dosimeters, and waited it out. They were fine. Their cumulative doses for the increment came in elevated but within limits. And that is exactly why the story matters. Because the procedure worked, which means the procedure gets used again. The mechanism behind the shelter is simple and slightly counterintuitive. You would assume the best shield is the densest material available. Lead, steel. It is not. When a high-energy proton strikes a heavy nucleus, it can shatter it, producing a spray of secondary particles including neutrons, which are themselves biologically damaging and harder to stop. Shield badly, and you can make the dose behind the shield worse than the dose in front of it. The material that works is hydrogen-rich and low in atomic number, because hydrogen nuclei are the same mass as the incoming protons, and absorb momentum efficiently without fragmenting into something works. Water works. Polyethylene works. Human waste storage containers, food, and stowage bags work, and are already aboard for other reasons. That is what shelter means in orbit. It means rearranging your supplies into a wall and sitting behind it. The other half of the system is on the ground, and it is the reason anyone gets warned at all. The NOAA Space Weather Prediction Center in Boulder, Colorado, operates continuously and issues alerts on scales you can look up yourself. R for radio blackouts, S for solar radiation storms, G for geomagnetic storms, each running 1 to 5. It draws on the GOES satellites in geostationary orbit, measuring X-ray flux and proton flux in real time, on SOHO, launched in 1995 and still operating, which watches the corona continuously, and on DSKOVR, parked at the L1 Lagrange point, roughly 1.5 million kilometers sunward, where Earth's gravity and the Sun's balance. DSKOVR is the tripwire. When a coronal mass ejection passes it, controllers get a direct measurement of the cloud's speed, density, and critically, the orientation of its magnetic field, which determines how badly it will couple with Earth's. That measurement buys between 15 and 60 minutes of hard warning. For the plasma cloud, that is enough to shut down vulnerable systems. For the protons, it is already too late. The protons left with the light. The January 2005 event demonstrated this precisely. On the 20th of January, an X7 flare produced the fastest rising ground-level enhancement recorded in modern times. The particle flux at Earth spiked within roughly 15 minutes of the flare's onset. 15 minutes from first detection to peak danger. If you are on the lunar surface, 3 days from home, 15 minutes is not a warning. It is a countdown you notice halfway through, which is why the current era changes the shape of the problem entirely. Solar Cycle 25 began in December 2019, and, contrary to early forecasts of a weak cycle, has run substantially more active than predicted, with peak activity through 2024 and 2025. On the 10th of May 2024, a series of coronal mass ejections from active region 3664 struck Earth and produced the strongest geomagnetic storm since 2003, rated G5, extreme. Aurora were photographed from Mexico, from southern Europe, from parts of the world that had never recorded them. Farmers in the American Midwest reported GPS-guided tractors losing precision mid-planting. Power grid operators in multiple countries took protective action, and aboard the ISS, the crew were once again directed into the more heavily shielded regions of the station and told to stay there. In 2024, not in a historical anecdote, 2 years ago, 7 people were told by radio to move to specific parts of their spacecraft and remain there because of what the sun was doing, and most people on the ground never heard about it because the aurora photographs were more interesting. This is not a rare emergency procedure. It is a recurring operational reality that gets used every solar maximum. So now hold 2 facts side by side. First, the ISS sits inside Earth's magnetosphere, which absorbs and deflects the overwhelming majority of what arrives, and even there, crews shelter. Second, humans are going back beyond it. Beyond the magnetosphere, there is no first layer. There is no deflection. Whatever the sun emits arrives at full strength, and the only thing between a body and it is whatever the vehicle brought along. We have measured what that costs, and the measurement is not an estimate. The Mars Science Laboratory, the mission that delivered the Curiosity rover, carried an instrument called RAD, the Radiation Assessment Detector, and it was switched on during the cruise from Earth to Mars in 2011 and 2012, sitting inside the capsule roughly where a crew would sit. Carrie Zeitlin and colleagues published the results in the journal Science in 2013. The crew's dose rate was approximately 1.8 millisieverts per day. Extrapolated to a round trip using that era's propulsion, the transit alone comes to roughly 660 millisieverts, before a single day spent on the Martian surface. Set that against the limit. In 2021, NASA adopted a single career radiation exposure limit for all astronauts, following a recommendation from the National Academies, 600 millisieverts, tied to a 3% risk of exposure-induced death. Compare the two numbers. The journey there and back, on a quiet sun, with no solar particle event at any point, exceeds the career limit before the mission objectives begin. And that figure describes only galactic cosmic rays, the constant low-level rain of high-energy nuclei arriving from outside the solar system, accelerated by supernovae over millions of years. They are not preventable. They are barely shieldable, because they arrive with enough energy that stopping them requires meters of material no launch vehicle can lift. There is a bitter irony in the physics here. When the sun is most active, its expanded magnetic field pushes more galactic cosmic rays out of the inner solar system, so the constant background actually falls. A quiet sun means a higher baseline. An active sun means a lower baseline punctuated by events that can kill you in an afternoon. There is no configuration of the star that is simply safe, which is why the Artemis program's approach is not to build a shielded ship, it is to build a shielded corner. Orion has no dedicated radiation compartment. What it has is a documented procedure in which the crew, on receiving an alert, rapidly reconfigure the cabin, stacking stowage bags, water containers, and equipment around the aft bulkhead area, to construct a temporary shelter, then get inside it and stay there for the duration of the event. It has been rehearsed on the ground. It takes minutes, which is roughly what the warning provides. On Artemis 1, the uncrewed test flight launched in November 2022, 2 anthropomorphic phantom torsos rode in the crew seats. They were named Helga and Zohar, and they were built from materials that mimic human bone, soft tissue, and organs, embedded with thousands of passive radiation sensors and dozens of active ones. Zohar wore a protective vest called Astrorad. Helga did not. The experiment, a collaboration between NASA, the German Aerospace Center, and the Israel Space Agency, was designed to answer a specific question. Does the vest reduce dose to the organs that matter most? The bone marrow, the lungs, the stomach, the ovaries. That data is now being analyzed and will directly inform whether crews on later missions wear one. That is the actual state of the art, not a force field, a vest, a wall of cargo, and a phone call from Colorado. So consider the worst case, fully spelled out, because it is not speculative and it is not remote. A crew is on the lunar surface, not on a short Apollo-style sortie of 3 days, but on an extended stay of the kind Artemis is explicitly designed for, a week or more, with EVAs scheduled most days. The moon has no magnetic field and no atmosphere. Standing on it, a person is exposed to raw interplanetary space, with only their suit between them and it. And a spacesuit provides very little shielding, because every gram of shielding is a gram someone has to carry in 1/6 gravity while doing physical work. An active region on the far side of the sun, invisible from Earth, rotates into view already unstable. It fires. The X-rays and the light arrive in 8 minutes and 20 seconds, and Boulder issues an alert immediately. The first relativistic protons are perhaps 20 minutes behind. The crew is 2 kilometers from the habitat, on foot or in a rover, with a warning measured in minutes and a return journey measured in tens of minutes. They will not make it inside before the flux arrives. That is not a failure of planning. It is a consequence of the speed of light being finite, and the speed of a walking human in a pressure suit being what it is. And then, if the event is a long-duration one like August 1972, the flux does not subside for days. The crew is inside a habitat with meaningful but not unlimited shielding, watching dosimeters climb, unable to go outside, unable to leave, with a return trajectory that takes 3 days minimum, and a launch window that may not open when they need it. This is why mission planners treat the shelter question as a design driver rather than a contingency, and why every serious lunar surface architecture includes proposals for burying habitats under regolith, several meters of it, because loose lunar soil is free, abundant, and works. For Mars, the problem gets worse in one specific way that people consistently underestimate: distance. At Mars's furthest, radio signals take up to 22 minutes each way. There is no consultation. There is no ground team talking a crew through it in real time. Boulder can send a warning, and the warning will arrive after the protons do. A Mars crew is not warned about a solar particle event. A Mars crew is informed of one they already experienced. The honest position on this, and it is worth stating plainly rather than dressing up, is that the radiation problem for long-duration deep space flight has not been solved. It has been characterized, quantified, bounded, and partially mitigated. Every major space agency publishes on it. The measurements are good, but there is currently no shielding technology, flown or near flight, that reduces galactic cosmic ray dose on a Mars transit to something comfortably inside NASA's own career limit. Active magnetic shielding has been studied for decades and remains at a low technology readiness level, because generating a field strong enough to deflect giga-electron-volt particles around a habitat requires power and superconducting mass that no proposed vehicle can carry. Pharmacological countermeasures, radioprotective drugs, are under genuine research and are genuinely uncertain. Anyone who tells you this is handled is telling you something the published literature does not support. What is solved, and solved well, is the acute case, the sudden one, the one that can kill in hours instead of raising cancer risk over decades. And the solution is exactly what those 2 men did in October 2003 and what 7 people did in May 2024. Get a warning, move, put mass between yourself and the sun, wait. Which brings this back to where it started, and to the thing that makes the whole subject stranger than it first appears. Everything about human spaceflight is built around the idea that space is hostile because it is empty. No air, no pressure, no heat. Every system on a spacecraft exists to hold back that emptiness. But the emptiness is passive. It does not change its mind. Vacuum today is vacuum tomorrow. and you can engineer against a constant. The sun is not a constant. It is a variable, unpredictable, magnetically violent object with an 11-year rhythm that it does not strictly keep, capable of releasing more energy in a few minutes than human civilization has produced in its entire history, aimed in a direction nobody can forecast until the active region rotates into view. It is the reason there is anything alive on this planet, and it is the single most dangerous thing in the neighborhood. And those two facts have never been in tension, because the atmosphere and the magnetosphere have been quietly handling it for 4 billion years. Take those away, put a human body in a metal can 300,000 kilometers from home, and the relationship reverses. The star stops being the thing that sustains you and becomes the thing you monitor, forecast, and hide from. That is the whole answer to the question in the title. Astronauts had to hide from the sun because at 400 kilometers up, the planet's defenses are already thinning, and the only remaining move is to put your own supplies between yourself and the light. They did it in 2003, they did it in 2024, and the procedure is in the manual, because in 1972, the sun fired at a window in the Apollo program and missed by 4 months. We are going back out there, further and for longer, in a solar cycle that has run hotter than forecast. The people planning those missions know all of this in far more detail than we've covered here. The shielding is being tested. The phantoms flew. The data is coming back. The star has not agreed to anything. If you want to keep track of this properly, subscribe, because we follow space weather as it develops, and this cycle is not finished. And if you want to know what happens when the same star aims at the ground instead of at orbit, watch the video on the Carrington event of 1859, when a solar storm set telegraph offices on fire, and operators kept sending messages with the batteries disconnected, powered by nothing but the current the sun was pushing through the wires. That one is next.